Okay, a question came up related to the video on lithostatic pressure, overburden stress. We were dealing with an integration problem, that integration problem that you see here. But the question was with regard to where does this expression for the density come from? And so we're just going to talk a little bit about how we get this expression here. So these are the assumptions that we made when we were working with this problem. If you want to take a closer look at this, you can go back to that video on lithostatic pressure and overburden stress and have a look at this and a couple other problems that are solved. But our main interest here is just to look at this expression and tell you where it came from. Porosity, we're just using a definition for porosity where we're assuming that the porosity, and that may or may not be a good assumption depending on the local geology, but let's say this is applicable. We're assuming that it's applicable in this area. So this is the kind of an expression you get when the porosity changes are due primarily to compaction. So we see the porosity decrease exponentially with depth from some reference depth. It could be the surface or it could be some boundary. And it could vary, between strata. But this is the relationship that we see up here just for the porosity. So to get it, how we get to this term up here, we're going to take a typical rock. It's got a lot of grains in it. It's got, water-filled pore spaces, and we're just going to squash all the grains down into the bottom of the cube. So we have a volume of grains, and then we have the volume of the fluid up here, and they're completely separated, and we can see what the separate volumes are, and so that's kind of just a visualization there. We want to show what the volume of the fluid and the volume of the grains are, and so we have a mass. This cube over here has a certain mass. It's related to the volume of the two components here, the fluid and the grains, and their densities. We know that the mass is equal to the volume of the grains times the density of the grains, plus the volume of the fluid times the density of the fluid. We also know that the volume of the grains is going to be equal to the total volume minus the volume of the fluid. So we know that the total volume is equal to the volume of the fluid plus the volume of the grains. So we have this expression over here. We substitute that in for V sub G, and we get that the mass is equal then to V minus V sub F times rho sub G plus V sub F times rho sub F. Then we just distribute the density through these two terms here, and we end up with this expression. Now, since the density is equal to the mass per unit volume, we're dividing the mass by the volume, total mass by the total volume, and we get this expression, just dividing both sides of the equation by V, and this gives us 1, so we have rho sub G minus V sub F over V times rho sub G plus V sub F over V times rho sub F. So, I should point out that V sub F over V, this term, is equal to the porosity. So we could replace minus phi plus phi. Minus phi times rho sub G plus phi times rho sub F. And that's exactly what we do over here. Recognizing this relationship, we have that the bulk density, the density of the total rock with the fluid and the grains taken together would be equal to the density of the grains minus the porosity times the density of the grains plus the porosity times the density of the fluid. That's by the porosity, we're just looking at this ratio, the ratio of the fluid to the. We're assuming that all the pore spaces are fluid filled, and we get this relationship here. We pull out a minus phi, and so we have rho sub G minus rho sub F. So we have the bulk density then is equal to rho sub G, the grain density minus the porosity as a function of depth times delta rho. This rho sub G minus rho sub F is just a delta rho. So we have density as a function of z is equal to rho sub g, and then we're just substituting in our phi of z here. In your area, you might have a different relationship. Maybe it would be linear, or it just depends on what's happening in the formation. Maybe you can't describe it analytically, but we're making that assumption here. And this is the term that you see in the integrand. And this is just, really what we've just gone through is an example of just kind of an equation manipulation tools combined with basic relationships between variables. So just as a point of clarification, I hope that was helpful, and we'll see you in other videos.